You click, you type, you swipe, and just like magic, a million things happen in an instant. But have you ever stopped and wondered, how? Like, really how? Well, we're about to take a journey inside that digital mind, from the big picture all the way down to the tiny little switches that make it all possible.
So, here's our game plan for today. First, we'll meet the team, the physical parts doing the work. Then we'll check out the blueprint that organizes them. After that, we're going to learn their secret language, see how that language describes our world, and finally figure out how a machine actually does math.
I mean, really think about it. What is the chain of events that happens when you click an icon and a program just appears? What does it actually mean for a machine to think or process information? That's exactly the mystery we're going to unravel.
All right, let's kick things off by, metaphorically prying open the case of your computer. Inside, there's a core team of components. We call them functional units, and they are responsible for every single thing that happens.
The easiest way to picture this is to think of a small, super efficient office. The input unit, that's your keyboard and mouse, is basically the reception desk, taking in new information. Then you've got memory, which is the office filing cabinet. The ALU, who's the math genius in the corner. The control unit, who's the manager running the whole show. And the output unit, your screen, which presents the finished project.
So the memory unit is that digital filing cabinet. It holds everything the computer is working on right now. But here's the really important part. It doesn't just store the data, like the words in a document. It also stores the instructions, the actual to-do list that tells the computer what to do with those words.
Now, let's meet the ALU. This is the office's resident math whiz. Anytime a calculation needs to happen, adding two numbers, checking if one value is bigger than another, that job goes straight to the arithmetic and logic unit. This is the number-crunching heart of the whole operation.
But who runs the show? Who tells everyone what to do? That would be the control unit, or CU. You can think of it as the boss or maybe a traffic cop. It grabs instructions from memory and just directs traffic. It tells the memory unit what to fetch, the ALU what to calculate, and the output unit what to show. It's the reason everything happens in the right order at the right time.
So we've met the team, but how are they all organized to work together so seamlessly? Well, it all comes down to a master plan, a brilliant blueprint from way back in 1945 called the von Neumann architecture. And believe it or not, it's still the foundation of pretty much every computer we use today.
See, before this, computers were clunky. They kept their instructions and their data in totally separate places, which made them super rigid. Von Neumann's idea was revolutionary, but also beautifully simple. Just store them together in the same memory. All of a sudden, the recipe book and the ingredients are on the same kitchen counter. This made computers flexible, powerful, and easy to reprogram. A total game changer.
And this architecture gives us a simple, powerful work loop that happens billions of times a second. First, the control unit will fetch an instruction from memory. Then, it has to decode it to figure out what it's supposed to do. Next, it sends that command off to be executed, usually by the ALU. And finally, the result gets stored back in memory. Fetch, decode, execute, store. That is the constant heartbeat of your computer.
Okay, so all these parts are humming along, talking to each other. But what language are they speaking? You might be surprised to learn it's an incredibly simple language. It really only has two words, on and off. Or, as you probably know them, 1 and 0.
And that's it. Seriously, underneath all the complexity, every single thing on your screen, every word, every color, every pixel, is just a very, very long sequence of these on and off electrical signals. It's like a giant wall of light switches, and every possible combination of switches being on or off represents a different piece of information.
And here you can see how our normal everyday numbers get translated into this new language. Our number 2 becomes 10. The number 5 becomes 101. It might look a little weird to us, but for a machine that can only think in terms of on and off, this is the most direct, logical way to count imaginable.
Okay, so we've got numbers down, but our world is way more than just numbers, right? So how does a simple on-off language deal with things like negative numbers, decimals, or even the letters you're reading right now? So, how do you write -5 using only light switches? You can't just draw a minus sign. Instead, engineers came up with a really clever system called 2's complement. It's basically a mathematical trick that lets the computer represent negative numbers in a way that allows it to do subtraction by actually just doing addition. It's a brilliant hack that makes the hardware a lot simpler and faster.
And what about decimals? Well, computers have two main ways of handling them. There's fixed point, which is great when the decimal point never moves. Think about dealing with money, for example. But for science or graphics where you need to handle huge or incredibly tiny numbers, they use floating point, which lets that decimal point float around to wherever it's needed.
And it's the same basic idea for text. Every letter, every symbol gets its own unique binary code. An early standard, called ASCII, was fine for English, but today our world runs on Unicode. It's a massive standard that assigns a unique code for pretty much every character in every language on the planet, and yep, that includes emojis.
So, we've said the ALU is the math brain, but we haven't talked about how it actually works. How does it add two numbers together using just ones and zeros? The answer lies in the most fundamental component in all of digital electronics, a little thing called a logic gate.
A logic gate is like a microscopic decision maker. It takes in one or more inputs, which are either a 1 or a 0, and based on one simple rule, it spits out a single output, which is also a 1 or a 0. These tiny things are the Lego bricks that build the entire digital world.
Let's look at the three most basic ones: and, or, and not. An AND gate is very strict. It only outputs a 1 if both of its inputs are 1. An OR gate is more relaxed. It outputs a 1 if at least one of its inputs is a 1. And the NOT gate is the simplest of all. It's just an inverter. It flips the input. A 1 becomes a 0 becomes a 1.
Now this is where the magic really happens. By themselves, these gates are incredibly simple. But when you start wiring them together, thousands, millions, even billions of them, you can build circuits that do incredible things. For example, if you hook up a few logic gates in just the right way, you can build something called a ripple carry adder, which is a circuit that can take two binary numbers and add them together.
And it just scales up from there. For more complicated math, like multiplication, computers don't just add a number to itself over and over. That'd be way too slow. Instead, they use really clever optimized recipes, like Boot's algorithm, to find shortcuts and get the answer in the fewest possible steps.
So, let's wrap this all up. Every computer has 5 core parts, organized by the von Neumann architecture. They all speak a secret language of ones and zeros, using clever tricks like 2's complement for negative numbers. And all of their incredible calculations are built from tiny, simple decision makers called logic gates.
And here's something to really think about. That basic blueprint from 1945, fetch, decode, execute, store, is, at its core, still how your phone, your laptop, and your smartwatch all work. It's gotten unbelievably faster and smaller, of course, but the fundamental idea is almost 80 years old. So it makes you wonder, what comes next? What's going to be the next big leap in how machines think?